Okay, hello grade 11s. Welcome to our next distance learning lesson. Today we're going to be continuing on in chapter 7. We're going to be in 7.3 and 7.4. We're going to extend on our learning from yesterday when we were looking at predicting mass of product and reactants. And we're going to be looking into how we can predict which reactant may be limiting or excess if that information isn't explicitly given to us in the question. Okay, so we are in 7.3 and 7.4 of your textbook. The specific pages, if you're looking for some extra help, is 326 to 335. Okay, so we're going to start off by talking about how much is just right, and then we're going to talk about how we figure out whether something is in a limiting reactant or an excess reactant. We'll do some practice problems together, and then I'll leave you some time at the end of the hour to do some practice problems yourselves. So by the end of the class, what you should be able to do is you should be able to predict if a reaction will go to completion, and this will include an assessment of limiting and excess reactants. All right. Okay, so a limiting reagent, we talked yesterday a little bit about excess reagent. If something is not an excess, it is limiting, okay? The limiting reagent is essentially what's going to run out first. So we see this every day. Again, we're all in social distancing right now. Maybe your groceries are only coming in once every other week like me. And so we're eating a lot more food that we can throw in the freezer and pull out later. So you may be eating things like hot dogs right now. And one thing you may have noticed that has frustrated people for years is that hot dog buns are always sold in a package of 8, whereas hot dog wieners, the actual meat part of the hot dog, is always served in a package of 10. So we know to make a hot dog, you need the meat and you need the bun. But in this case, we have more meat than we have buns. So what I'm going to run out of first while I'm making hot dogs, I'm going to run out of buns before I run out of the meat. Okay? I'm going to have 2 extra wieners left behind because I don't have 10 buns. So if this was a chemical reaction that meat plus bun equals a hot dog, what would be limiting would be my bun. That's what's going to run out first. What's going to be in excess is the meat. That's what I'm going to have extra of left over at the end of my reaction, okay, or building those hot dogs. Same thing happens in chemical reactions. When we mix 2 things together, they're very rarely in perfect stoichiometric ratios, or exactly what we need of each. Almost always, one thing's going to be limiting. We're going to run out of one thing before the reaction comes to completion, which means the other thing is going to be excess. I'm going to have extra of it. So when we're calculating how much product we're going to make, we need to consider what's my limiting reactant and what's my excess reactant. Like in this case, even though this says it has 10 servings of meat, I can't actually make 10 hot dogs because I only have 8 buns. What determines how many hot dogs I'm going to make is my limiting reactant, which in this case is the buns. Okay. So the limiting reactant or reagent in any chemical reaction is the one that is entirely consumed. So we run out of completely, just like previously with the hot dogs, buns, when the reaction goes to completion. Okay, if one reactant isn't limiting, it must be in excess. Okay, just like the meat in the previous example. Whatever you have extra of left over at the end, that's going to be your excess reactant. And we can calculate this very easily just by building on those exact same equations and formulas and setup that we did yesterday. Okay, so I'm going to make myself disappear again so I can show you some notes. Okay, so this question says, what is the limiting reagent in the synthesis of AlOH3, aluminum hydroxide, from the reaction of 13.4 grams of aluminum chloride with 10 grams of sodium hydroxide? Okay, so we have here, we need our balanced chemical equation. So we're going to have AlCl3 reacting with, let me leave myself some extra room actually, sodium hydroxide. Okay, we should remember from unit 2, this would be a double displacement reaction. Okay, so these guys are going to switch places. We're going to have sodium now with chlorine. Whatever is first is now with last. Sodium has a charge of +1, chlorine has a charge of -1. So if we crisscross those, it stays the same. Okay, 1 and 1. Plus aluminum is now going to be with hydroxide. Now, if we look on the periodic table, aluminum has a charge of 3 plus, hydroxide has a charge of 1 minus, so that's going to give us our AlOH3. Okay, to balance this, we'll look at metals. We have 1 aluminum and 1 aluminum. We have 1 sodium and 1 sodium, so our metals are balanced. We have 3 chlorine, our nonmetal. We only have 1 over here, so we need to make this a 3. And we have 3 hydroxide and only 1 over here, so this needs to be a 3. And we've also now changed our sodiums to 3 and 3. So we're now balanced with 1, 3, 3, 1, right? 1, 3, 3, 1. Okay, so we're going to set up our buildings. Mass, molar mass, moles. Okay, and it says, in this case, it's a little bit different. It says, it gives us our mass of 2 products. So 13.3 grams, 13.4 grams of aluminum chloride that's given to me. So I'm going to put that in mass with 10 grams of sodium hydroxide. Okay. So we're going to say, what am I going to run out of first? Okay. So when I go over into my products, now because it's just asking me what my limiting reagent is, it doesn't matter either one, but I'm going to see what's going to make less. It doesn't matter if you do sodium chloride or aluminum hydroxide. I'm just going to do sodium chloride because it's first in my equation. What's going to make less sodium chloride? We don't actually need to know the mass. We could just say compare the moles. Just like in the previous example, we said what's going to make less hot dogs? 8 hot dog buns or 10 hot dog wieners? Well, the meat is going to make 10 hot dogs, whereas the buns are only going to make 8. So what's limiting is the lower number. So that's going to be the buns. In this case, what we're going to do is we're going to see how much sodium chloride could aluminum chloride make, and how much sodium chloride could sodium hydroxide make. Whatever can make less is going to be our limiting reagent. So how are we going to do that? To get over into our product side, we're going to have to do our mole ratio. So we're going to have to go down our buildings and divide. So first thing I need to do is I need to calculate my molar masses. So for aluminum chloride, if you look on your periodic table, aluminum weighs 26.98 grams per mole. And we have 3 chlorine, each which weigh 35.45 grams per mole. So that's going to give me a molar mass of 133.33 grams per mole. Sodium hydroxide, on the other hand, okay, sodium has a mass of 22.99 grams per mole. Oxygen has a mass of 16 grams per mole, and hydrogen has a mass of 1.01 grams per mole. So that's going to give me 40 grams per mole. Okay, so first thing I'm going to do, because I'm going down for both of these to the main floor, I'm going to divide. So I'm going to figure out moles of aluminum chloride and moles of sodium hydroxide. So my moles of aluminum chloride is going to be 13.4 divided by 133.33, which is going to give me 0.100 moles. Sorry, 1.01 moles, if I round it. And 10 divided by 40 is going to give me 0.250 moles. Now, it's not which one of these two numbers is smaller, it's which one is going to make less of this. So we need to do mole ratios of this and mole ratios of this to see which makes less, because it's not always what you have less to start with, okay? It may be just, it's always what is going to end up making less at the end. And that's going to be different depending on what those mole ratios are. So you have to calculate the mole ratios for each of those. Okay, so let's start off by figuring out aluminum chloride. Okay, I want to know how much sodium chloride I can make from aluminum chloride. So I'm going to put my mole ratio of sodium chloride on the top and my mole ratio of aluminum chloride on the bottom. So I know I can make 0.101 moles of aluminum chloride, and I'm going to multiply that by 3 sodium chloride for every 1 aluminum chloride. So I'm going to multiply that by 3, so that's going to give me 0.303 moles. Okay, so if I use up all of my aluminum chloride, I should be able to make 3.03 moles of sodium chloride. Same thing, I'm going to figure out how many moles of sodium chloride can sodium hydroxide make. Okay, to do that, I got to put what I want on the top, which is sodium chloride, and what I have, sorry, this isn't moles, this is mole ratios, what I have on the bottom. So this, I have a quarter of a mole. I'm going to multiply that by 3 over 3. 3 sodium chloride for every 3 sodium hydroxide. So 3 times 3 over 3 is the same thing as 1, so I'm going to make the same. So what this is saying is if I use up all my aluminum chloride, I'm going to make about just under a third of a mole of sodium chloride. But if I use up all of my sodium hydroxide, I'm only going to make a quarter of the mole. Okay, so even though I started with more sodium hydroxide, we can see it actually makes less sodium chloride than the aluminum chloride does. Now, I don't have enough sodium hydroxide to make a third of a mole of sodium chloride. I don't have that much, which means I'm going to run out of sodium hydroxide first. Okay, so I would say because 0.303 is greater than 303 moles is greater than 0.250 moles. Okay, that means sodium hydroxide is limiting. Okay, this is my limiting reactant. Okay, essentially what I'm saying is I'm going to run out of sodium hydroxide first. I'm going to run out of it because it can make less. Just like with the hot dog buns and the meat from the hot dog, I can make less hot dogs from the buns, so that's going to be limiting. Okay, so because I'm going to make less sodium chloride from sodium hydroxide, that is what's limiting. Doesn't matter that I actually had more of it to start. What matters is it can actually make less. And that has to do with those mole ratios up at the top. So that also means AlCl3 is therefore what? Well, it's in excess. I have extra of it. Okay, I have about 0.05 extra of it because it can make more sodium chloride. Okay, so what you're going to do is you're going to compare those two values. Because this one is less, I'm actually in practicality only going to make 0.250 moles because I don't have enough sodium hydroxide to make the 0.3 moles. So this is limiting. This is in excess. Okay. Let's try another one. It says, in the synthesis reaction which forms sodium chloride, what would be the limiting reagent if 0.1 moles of sodium reacted with 0.1 moles of chlorine? Well, in the synthesis reaction, synthesis of sodium chloride would be sodium plus chlorine. And again, chlorine is going to be Cl2 because it's one of our Hofbrinkel gases, if you remember from Unit 1, HOFBRINCL. Okay, it's going to make sodium chloride. So we'll set this up, mass, molar mass, moles. Okay, so it says 0.1 mole of sodium. So my moles here is 0.1 moles reacted with 0.1 mole of chlorine. And remember, we need to start with a balanced chemical equation. So we need to have 2 of these and 2 of these to balance the equation, right? Because we had 2 chlorine and only 1 over here, so we need to put a 2 here, which means we need to put a 2 here. So it says, what's going to be the limiting reagent? Well, I'm going to figure out how much sodium chloride can each of these make. Whatever can make less is going to be limiting. Okay, so I'm going to say how many moles of sodium chloride can I make if I use up all of my sodium? I'll do that, like always, using my mole ratios. Oops, that's the wrong one. Oh. Sodium chloride, sodium. So they're told in the question I have 0.1 moles. If I look at my mole ratios, I have 2 NaCl for every 2 sodium. That's going to give me the same. I can make a tenth of a mole, 0.1 moles, of sodium chloride if I use up all of my sodium. Now, how many moles of sodium chloride can I make if I use up all my chlorine? Well, I'll do the same thing here. I'll put in my mole ratios. Okay, so I also had 0.1 mole, but if I look now, my ratio is 2 over 1. So I'm going to be able to make twice as much. Now, what that's saying is if I use up all of my sodium, I can make 0.1 moles of sodium chloride. And if I use up all of my chlorine, I can make 0.2 moles. So this makes less. So that means sodium is limiting. It makes less NaCl. Okay, because 0.10 is less than 0.20. That also means that Cl2 is in excess. We have extra, we're going to have extra unused chlorine left over in this reaction. Okay? So I calculated my product, how much each can make, and whatever can make less, in this case, sodium is limiting, and chlorine is going to be in excess. This is because sodium made less NaCl and chlorine made more NaCl. Okay, we're comparing the two numbers that we predicted right here. Okay. Now it says how much was left over of the excess reactant in the previous question. Okay, so if we look at our question here, we had sodium and chlorine making sodium chloride. Okay, we had a 2 here and a 2 here. Mass, molar mass, mole. Okay, we had 0.1 of this, we have 0.1 of this, and if we look in our prediction, we're actually only going to make, we're always going to make the lesser value. We're only going to make 0.1 mole of this. Okay, we know this was limiting, and this was in excess. Okay, so it's asking you how much was left over. So we'll do that in mass. Okay. When it says how much, you can clarify. In this question, we'll assume it's asking for mass. You could also report it in moles. If it was a test or a quiz or exam, you could just clarify with the teacher. Okay, so what we're going to see is how much of this, we know there's going to be a bunch left over, but how much is left over? Well, we can just do that by figuring out how much did we actually use up. So if we actually only produce 0.1 moles of sodium chloride, how much of chlorine do we have to use up? So how much chlorine is actually used if we use up, or if we produce all of the sodium chloride that we expect to? Okay, so we'll do our same mole ratios. In this case, if I actually make 0.1 mole, which we predicted, because that's how much the limiting reactant makes, that's how much we're actually going to have. Just like before when we said 8 buns can only make 8 hot dogs. Okay, we're actually saying now, okay, well, if we actually only make 8 hot dogs because we have extra leftover meat, how do we figure out how much leftover meat we have? Well, we would say, well, if I'm only making 8 hot dogs, how many meat are used up in 8 hot dogs? Okay, so that's what we're doing here. We're seeing how much of this am I actually going to use up to produce this value. that I predicted using my limiting reactant, right? This is the value I predicted right here. Okay, so my mole ratio is 1 chlorine right here for every 2 sodium chloride. Okay, so 0.1 times a half is going to be 0.05 moles. So I'm actually going to use up 0.05 moles of chlorine to produce 0.10 moles of sodium chloride. So I'm actually only going to use 0.5 moles of my 0.1 moles available to me. So what's going to be left over? So the moles of chlorine left over is going to be, how many moles of chlorine did I start with? And how much did I actually use? Well, I started with 0.10 moles. That was given to me right here. I only used 0.05 moles. That's what I calculated here. So I'm going to have an extra 0.05 moles. This is not used up. Okay? You could even tell me how much that weighs. So we know the mass of that chlorine is going to be moles times molar mass. I have 0.05 moles left over. And the molar mass of Cl2, chlorine weighs 35.45 grams per mole, and I'm going to multiply that by 2, which is going to give me 70.90 grams per mole. So that means I'm going to have 3.55 grams of Cl2 left over. I figured out how much was left over by saying, how much did I start with? How much did I actually use up? I actually only used up, I calculated here, 0.05. And that's the same as saying 3.55 grams of sodium chloride. Okay, now limiting and excess reactions, if we just mix them together like we've seen, we can calculate the different values pretty easily using the same rules as yesterday. Sometimes though, we purposefully want one of two reactants to be limiting or in excess. So let's say, for example, I work for a company and I'm producing a chemical, okay? And let's just say it's really simple. I work for a company that says A plus B makes this C, and this is the product I sell. Okay? So I'm making C at a lab for money, like it's a medicine or a cleaning product or whatever. And let's just say ingredient A is really inexpensive, and ingredient B is very expensive. So this costs me a lot of money, this ingredient B. When I'm setting up my reaction, I may want to make sure that this ingredient A is in excess because it doesn't cost me as much, so it doesn't matter if I have leftover A that didn't get used up, and I really want B to be limiting because it's so expensive. I don't want to waste any. I don't want any left behind like we saw in that previous question. Okay? So I may have something that I really want to make sure is in excess, and another thing is limiting. Okay? Essentially how you would do this is we've learned how to calculate how much of something we need for a reaction to go to completion, and we also now can determine what's in excess or limiting. What I may want to do is if I want to make sure that this is in excess and this is limiting, I may add to the amount of ingredient I need 10% of A and purposefully add extra to make sure that this stays limiting. Okay, so if I work at a chemical company and I'm saying I really need to make sure A is in excess, I may calculate how much I actually need for the reaction to go to completion, and I'm going to say, you know what, to make sure that I don't waste any of this really expensive, valuable product, I'm going to add an extra 10% to this guy to make sure it's in excess. So I'll show you how this would work out in calculations. So it says you want to ensure 2 grams of copper 2 sulfate reacts completely with an excess of sodium hydroxide. So we know for a fact we want this to be limiting. It would likely be something with a metal like copper in it, which is a precious metal, is going to be a lot more expensive. So if I work at a company, I may say, I want to make sure that this is limiting, and I want to make sure this is in excess, like the question said. It said, what would be a reasonable mass of NaOH to use? Okay, so remember, because I want NaOH to be in excess, I'm going to add about 10% extra mass to make sure that reaction goes to completion and ensure that this is in excess and isn't limiting. So I don't waste, okay? I don't want any waste of this product. Okay, so I'll put it together. So we'll have to start off with our chemical equation. We have CuSO4, copper 2 sulfate, plus sodium hydroxide. Now this is going to be a double displacement reaction. We're now going to have sodium sulfate, and remember, sulfate has a 2 minus charge, sodium has a 1 plus charge, so it's going to be Na2SO4. Okay, and we're going to be left with copper. Now I know this is copper 2 because this is a 2 minus, this must have a 2 plus charge to cancel out those numbers. Hydroxide, so it's going to be CuOH2 because this is a 1 minus. So when you crisscross the charges, you're going to have CuOH2. So like we learned, we always have to start with a balanced chemical equation. So we have 1 copper, 1 copper, we can keep that the same. We have 1 sodium and 2 sodium, so we need a 2 here. We have 1 sulfate and 1 sulfate, so that's good. And now we have 2 hydroxide and 2 hydroxide, so we're now balanced. Okay, so we'll set up our tables. Mass, molar mass, moles. It says we have 2 grams of copper 2 sulfate, and it's saying how much of this do we need? When we figure out how much we need, we're going to add 10% to it after, okay, to ensure that this is in excess. So we're going to do the same thing we did before. We're starting in mass. We need to get down to the first floor. So we're going to divide by molar mass. If I take a look at that, I need to calculate that. Copper's molar mass is 63.54. I'm going to add to that the molar mass of sulfur, which is 32.06. And I'm going to add to that 4 times the molar mass of oxygen, which is 16. If you put that in your calculator, you're going to get 159.6 grams per mole. While we're at it, we can calculate the molar mass of sodium hydroxide because we are going to need it. Sodium is 22.99, oxygen is 16, and hydrogen is 1.01. So that's going to give us 40 grams per mole here. Okay, so we're going down, so we need to divide. So 2 divided by 159.6 is going to give me 0.013 moles. Okay, so to get how many moles of sodium hydroxide we would need, we're going to use mole ratios we did yesterday because we're trying to get up to this top floor. So we want to know moles of sodium hydroxide. We only know moles of copper sulfate. So we're going to multiply that by our mole ratios. What we want is on the top, and what we have is down at the bottom, so we can cancel out those units. 0.013 moles times 2, because we have a 2 right here, over 1 copper sulfate. So it's going to give us 0.026 moles. All right, to get a mass, we're going up, so we need to multiply. So 0.026 times 40 is going to give us 1.04 grams. Now, if we only put in 1.04 grams, that's exactly how much we need. But we said we want to ensure that sodium hydroxide is in excess. So what I'm going to do, instead of adding just 1.04 grams, I'm going to add 10% to that. So the mass of sodium hydroxide I'm actually going to get is the mass needed, but I'm going to multiply that by 1.1, okay, because that's adding 10%. Okay, if I multiply it by 1, that's just 100%. That's exactly what I need. If I multiply it by 1.1, I'm adding 10% to that. So what I actually only needed was 1.04 grams, but I'm going to multiply that by 1.1 to get an extra 110% of what I actually need. So that's going to be 1.14 grams. Okay, so what I would say is, to ensure CuSO4 is limiting and NaOH is in excess, I would add 1.14 grams of NaOH to 2 grams of copper 2 sulfate. By adding that extra 10%, I'm ensuring that I have extra of this. I've added a little bit extra. That's going to ensure that this is in excess and this is limiting. Okay? And that's going to serve my purpose. All right. What I would like you to do now is I want you to start practicing some of these problems. Okay? So these are some questions from your textbook that you can take a look at. Okay? Again, remember that there is answers at the back of your book in Appendix C. Okay? And if you have any questions on how to answer them, you can contact me by email. And again, as you know, the easiest time to get a hold of me is during office hours, but I am available throughout the day, throughout the school day. Okay? Thanks so much, and I hope everyone's staying safe, staying healthy, and staying home.